You know that feeling, right? You write a perfectly good function and then you have to copy-paste it just to change int to double. Well, if that sounds familiar, you're in the right place. Today, we are diving deep into one of C++'s most powerful features, templates. We're going to take that common coding headache and turn it into something super elegant. So, here's the game plan. First, we'll talk about that pesky repetition problem. Then, we'll look at the big idea, the generic solution. After that, we'll get our hands dirty with function and class templates. And to wrap it all up, we'll see how it works in a real data structure, stacks. All right, let's kick things off with a frustration I think every single programmer has felt. I'm talking about repetition. You know the drill. You write some brilliant piece of logic, and then what happens? You find yourself copying and pasting it, once for integers, again for floats, maybe another time for strings. Ugh. Seriously, think about it. How many times have you written a function to, say, add two integers, and then immediately had to write the exact same function again just for two doubles? It's not just inefficient, it's a total maintenance nightmare down the road. And this right here, this visualizes the problem perfectly. Take a look at the left side. You've got separate add functions for integers and floats. It's the same logic, just duplicated code. Now look to the right. That's our goal. A single, clean, generic function that handles both. This is literally the before and after picture we're shooting for. Okay, so the big question is, how do we get from that cluttered before state to that beautiful, clean after? Well, the answer isn't some complex trick. It's actually a really powerful programming philosophy, the idea of writing generic code. This core idea is called generic programming, and really, it's pretty simple when you break it down. Instead of writing your code for one specific data type, like an int or a string, you write generalized code that can work with any data type. You just define the logic once, and you let the compiler do all the heavy lifting for you. And the benefits? Oh, they are huge. I mean, of course you get code reusability and way less duplication, that's the obvious one. But what's really cool is you also get type safety. The compiler is still checking everything for you at compile time, so you're not sacrificing safety for convenience. All this adds up to code that's just way easier to maintain and so much more flexible. So in the world of C++, this idea of generic programming isn't just a philosophy. It's a concrete feature called templates. And as you can see, templates basically come in two main flavors that we're going to break down. Function templates for making generic functions, and class templates for making generic classes. All right, let's dive into our first type, function templates. This is all about creating that one, single, reusable blueprint for a function that can handle a whole bunch of different data types. Okay, check this out. Here is our generic add function. The real magic is happening in that very first line, template class T. That little line tells the compiler, hey, what follows is a template. And that letter T, think of it as just a placeholder, a stand-in for any data type. Then you see the function uses T for its parameters and its return value. It makes the whole thing totally type agnostic. Now this is where it gets really cool, when we actually use it. When the compiler sees you call add 2, 3, it's smart enough to say, those are integers, and it generates an integer version of the function right on the spot. Then, when it sees add 2.5, 3.5, it does the same thing but for doubles. So you write one template and the compiler becomes your personal assistant, creating as many specific versions as you need, all automatically. But wait, there's more. Templates can get even more flexible than that. You're not just limited to one generic type. Look at this display function. It's using two placeholders, T1 and T2. So what does this mean? It means you can pass arguments of totally different types, like a string and an integer, into the very same function call. How powerful is that? Okay, so we've seen how awesome templates are for functions. Now let's take that exact same powerful idea and apply it to classes. This is where we start building reusable blueprints for our data structures. And you'll see we're right back at the same old problem, just in a new context. Let's say you need some kind of box container to hold stuff. Without templates, what would you do? You'd have to make an int box class, then a float box class, then a string box class. It's that same old story of redundant code all over again. And you guessed it, the solution is a class template. It works just like with functions. We use that template class T line to declare a generic box class. Then inside, you see the member variable value is of type T. And just like that, this single class definition becomes a universal blueprint for a box that can hold any data type you want. Now, the syntax for actually creating objects from this template is super important. You see those angle brackets? That's where we tell the compiler what specific type we want to use. So when we write box subint, we're telling the compiler, hey, go ahead and create or instantiate a version of the box class just for integers. Box subdouble does the same for doubles, and you can do this for any type you can think of. And yep, just like we saw with functions, class templates can also juggle multiple generic types. Take a look at this pair class. It uses T1 and T2, so it can hold two values that might be completely different types. This means you could create a pair int float or a pair string int, all from that one single class template. All right, we've gone through the theory for both functions and classes. Now it's time to see how this all comes together in a real-world practical example. We're going to use a classic data structure to do it, this stack. So what you're seeing here is a full C++ program that uses the generic stack class, which is part of the standard library. What we're doing is creating two different stacks, st1 and st2. For this example, they're both going to hold integers. So let's walk through what the code is actually doing, step by step. Okay, first up, the program builds the first stack, which we're calling st1. It uses the push method to add 4 integers onto it. The best way to picture this is like a stack of plates. 51 goes on the bottom, then we put 52 on top of that, then 53, and finally 54 is sitting right at the very top. Okay, what's next? The code calls the pop method. Now, stacks have a rule, last in, first out, or LIFO. That means the very last plate we put on the stack, which was 54, is the first one to be taken off. So after we pop, 54 is gone, and the new top of our stack is 53. Now the program moves on to our second stack, S2. It pushes 4 new values onto that one. So let's pause and see where we are. At this exact moment, the top item on S1 is 53, and the top item on S2 is 14. Got it? And now, for the grand finale, the code calls a single function, stack1.swap_stack2. Because the stack class is a template, its swap method knows exactly how to exchange the contents of these two objects, no questions asked. And look at the result. The top of stack 1 is now 14, and the top of stack 2 is 53. They've completely traded places. That is the power of generic code right there in action. So when you boil it all down, templates are what let us write code that's flexible, powerful, and still totally type-safe. They do this by letting us separate our logic from the specific data types we're using. Honestly, they're a cornerstone of modern C++. So I guess the only real question left is, what cool things are you going to build with them?